Yes, okay, perfect. Yeah, I was not familiar with that. So thank you for the introduction and welcome to my talk. It's about the new BPM system for PETRA 4, or rather it is a summary of a bachelor thesis of Jonas Lamarck, which was a student who worked at DESY. So this talk is split into 4 parts. In the first part, I will give a short introduction of the history of PETRA, as well of the current PETRA 4 project. While in the second part, I will take a closer look at the new BPM system for PETRA 4 and its requirements. In the third part, we will see some measurements which were taken with said systems and we see the setups and the results of it. This all will be rounded by a conclusion. So first coming to PETRA, which stands for Positron-Electron Tandem Ring Accelerator, and it developed over the years quite a bit. So in the beginning, it started out, as the name says, as a particle collider, actually. And in 1988, it became the pre-accelerator for HERA. And with the shutdown of HERA in 2007, it was changed so that it is a dedicated third-generation light source, which is running right now. Here you see a picture of the tunnel on the DESY campus. And currently, we are working on upgrading these PETRA 4 light source into a PETRA 4 light source, which will be coming to now. So PETRA 4 will be quite a big upgrade. Here you will see a schematic of PETRA 4. So large parts of the tunnel will be reused. So you will see the circumference of 2.3 kilometers stays the same. And the injected chain of LINAC and DESY will also be refurbished, but in principle stay the same and will lead to an energy level of 6 giga-electron volts. One of the most noticeable things about the upgrades is that the emittance is reduced quite a lot from 1.300 picometer radians to below 20 or 50, depending on the operation mode. And besides that, there will be a lot of constructions here in the west. The halls in the east will be reused, but there will be some new beam lines added and refurbished as well. So now we will come to the system itself, since such an upgrade, of course, infers changes into the BPM system as well. So one thing noticeable is the steep increase of the number. So there will be 800 BPMs installed. And combined with the large radius of a facility, that means many long cables which will not be able to be fit in the tunnel and therefore will be thermally uncontrolled and thus need to be compensated by external crossbar switching, which is used to compensate the effects of the temperature drift of such an unstable environment. So this work focuses on mainly 4 parameters, which are required for PETRA 4, which are the long-term stability, the closed orbit resolution, the beam charge dependency, and the single-turn resolution. Coming to these requirements, here's a disclaimer. The work was not done by myself, but by said student Jonas Lamarck, and he did all the measurements and setups to see if these requirements are fulfilled. So we come to the setup. Let's start at the top left. Here we have 2 BPMs with their 4 plate signals, which then are led into the external switch matrix so that the long cable distances can be compensated for and the deswitching matrix will be part of the retransition module. This system will be the cards we saw earlier, while for the system there are still the FMC to subboard. It will be exchanged into the unisubboard, which Michael presented earlier. And these 2 cards are fitted into one slot in the micro-DCA4 environment and then connected via the backplane to the micro-DCA carrier hub and to the CPU with the programs. Now that we know the setup, let's go to the measurements. Since Since PETRA 4 is not built yet, we tested it at PETRA 3. So we took an existing BPM in an accelerator, which is in the live operation, and built in a splitter. So one part goes to the Libera Brilliance, which is the normal readout unit for PETRA 3. And one part we sent to the switching matrix with the micro-DCA system in the back of it. The measurement includes, of course, the plate signals, but is also dependent on the monitor constants, which were for the measurements of the four requirements were said to be 10 millimeter, even though it needs to be said that the monitor constant of PETRA 4 is below 10 millimeters, so this is a worst case study, so to say. Here you see the setup in the tunnel, or on the left side in the tunnel. Here are three sets of the four BPM plate signals, which you can distinguish by color. One coming from the BPM system itself, one leading to the Libera Brilliance, and one leading through the switching matrix, which was also mentioned in another talk, and then be sent to the micro-DCA quetch, which are seen here. So from the front, it looks rather clean, not many cables, but when you see the back, there are quite a lot of cables for the Ethernet connection as well as for the signals themselves. So when we did the first measurements, we encountered this. So you see here the comparison of the micro-DCA and the Libera. And you see there's a slight offset, but what is more interesting is that there's quite a lot of oscillation, and there are also these jumps which happen after injection. So what we can see from here is that, of course, we do not only measure the performance of the system itself, but we measure the beam motion, which we are not interested in for a study of readout systems. So we had to change the setup to this. So now a system does not get all four plate signals, but only one, which is be split into four parts. That has the merit that we don't see any beam movement, and all the signals are the same, only for the differences that are introduced by the system itself. So any positions or so we see are just the system itself and not the beam movement. But of course, the setup has its price. One is that now this BPM is not part of the live operation of PETRA 3 anymore, as the Libera Brilliance cannot read any actual position data. And we also use less power. So here we utilized only one plate as in comparison to four. So we will have a lower signal noise ratio. So again, the measurement will be worse than what you will actually have in the end. So we have quite some safe space when looking at the results. Here on the top, you will always see the measurement setup as a reminder that it's measured in this way. And here we have the first parameter, the long-term stability, which is required to change less than 1 micrometer over 6 days. Here you see the two different operation modes, one with 480 bunches present in the machine and one with 40 bunches present in the machine. Okay, I don't know if it's readable from the back, I think not. Here it's 100 nanometers and here's minus 200 nanometers, which is well below 1 micrometer. And here it's minus 100 to 50 for the 40 bunch mode. So you can see the requirements are well fulfilled. And there are also some temperature measurements taken to see if there is any relation between the temperature and the measurement data. But we see that the temperature only changes minor, so between 0.1 and 0.2 degrees over the whole time frame, and that there are no visible correlations to the measurement data. So, interesting. Yeah, great. Okay. So for the second parameter, the closed orbit resolution, it was measured again in both operation modes of PETRA. Noticeable, you see a dip here, but which is expected. It is the notch filter of the Libera system, which is used to suppress the switching frequencies from the crossbar switching. And when you integrate this noise data over the frequency, you will get an accumulation of the actual noise power, which will translate into the RMS value. So for 480 bunches, it's fine. It's at 1 kilohertz, approximately 70 nanometers, which is below 100. But with the current setup, or the setup at that point for the 40 bunch mode, there's actually an RMS of 174, which is above the threshold. So, here the animations work and the other slides not. Interesting. So we took a closer look at the automatic gain control scheme. So what you see here is the gain scheme of a part of the Libera, which, depending on the input power level, switches an attenuator so that the input power level stays inside certain boundaries. And it was not adapted yet to the operation of PETRA 4. So here you see the default gain scheme. So let's say there's an input power of minus 40 dBm or below minus 40 dBm, there will be no attenuation. If it's below minus 40 and minus 25, there will be an attenuation of 3 dB and so on. So for the measured data, there was an attenuation of 12 dB, which you see here, which is approximately the 174 we saw last slide. So if we disable this gain scheme and set the attenuation manually, we see that, of course, the signal power will increase, and thus the signal to noise ratio will also increase, and so the RMS goes down. So if we change the attenuation, we'll actually be below the threshold of 100 nanometer. So when we adapt the gain scheme to our needs, then it is also, the second requirement is also fulfilled for the 40 bunch mode. Coming to another parameter, which is the beam charge dependency, which should stay below plus minus 2 micrometers over 60 dB range. Unfortunately, PETRA 3 does not have this large range of power, so it was done in two separate measurements, one in the 480 bunch mode, one in the 40 bunch mode, because the power can be high in the 40 bunch mode. So if you combine these two power levels, we'll end up covering a range of 37 dB, which is the best that could be done with live measurements. And to see also that it is well below micrometers. So here it is 0.1 and goes down to minus 0.3 and similar dimensions on the other side. One thing that is noticeable is here are the jumps of data here, which can be related to the gain scheme I mentioned before, because these are the power levels where it's actually switching the attenuation and thus leading to this behavior. So coming to the last of the four parameters, which is the single turn resolution. This was measured in a special operation mode, so not the 48 bunches or 180 bunches mode, but rather injecting one bunch into the machine, letting it do one circle, and then dumping it immediately. This was done 100 times, and for each of these circles, the position was measured. Well, it's not an actual position, but the data was taken. And the RMS values are for the horizontal position 17 micrometer, and for the vertical position 18 micrometer, which are below the 30 micrometer which are required. So let's conclude this talk. All the four requirements I mentioned were fulfilled for a monitor constant of 10 millimeters, and the gain scheme of the automatic gain control will need to be adapted for the needs of PETRA 4. The system that was introduced is based on DESY4 and features also the external crossbar switching matrix for the long cable paths. And that's about it. Thank you very much for your attention.
Okay, before lunchtime, we'll go for questions. Do we have any questions?
for the presentation. So you showed that all the requirements were fulfilled. So my question here is, could you do any detailed test of the effectiveness of crossbar switching matrix? So like how well it compensates for the temperature drifts or for any disturbances? You have very long cables.
Not as far as I know. So the setup in which all the measurements were done were in a temperaturely controlled environment. The cable pairs were like, I mean, one side was in the PETRA 4 tunnel and the other one was in the neighboring hall. I don't know how long exactly the cables were, but I think it's like something 150 meters or so. But yeah, they were not put through a hard temperature drift test as far as I know.
But you also don't know how much the temperature varied in that 100 or so meters?
I mean, there was one slide. Oh, sorry.
Yeah, go back. Oh, back. No, the other side.
Yeah, I get it. Yeah, so the temperature was, of course, not measured through all positions, but it was measured on the switch matrix itself because it's the most temperature-sensible component. And here you see it is, well, I don't know if you see it. Here it's 20.8.4 and 20.9. So it's really small temperature variation here. So yeah, there was no test for a harsh environment as far as I know.
Do you plan to stress the system in that direction, like to see how it behaves with larger temperature variations? Of course, not with the switch matrix because it's in the tunnel, but
yeah.
Cables, for example.
I mean, for that we would. I don't know if it's planned. I mean, I'm presenting the work, but I did not do it myself. But I imagine that for that you would need the cable structure and everything and have place to lie it outside. So I think the setup would have quite some effort. So I guess there's nothing planned in the near future.
One question.
Yes?
You are presenting something that another student did.
Yes.
How is this? How do you see this knowledge transfer? So you just got the measurements, so there was some knowledge transfer from the student, or he just left and then it's up to you just to understand this thing.
Exactly. I mean, he did his bachelor thesis and now returns to a study of his master course. So he's not right now part of DESY anymore, so we can't just ask him, yeah, please present your work. So it was done by me. And what was your question exactly?
There was any knowledge transfer from that student to you, or you just read the measurements?
How I did. I mean, we worked at some points together, so when he had trouble, he came to me, but most of the details were unknown to me. And I read through his thesis. I talked to Gero, who supervised him, for things that were unclear, and tried to pick this all together to get a whole picture myself.